Hi, scientists. In this screencast for task-specific clarification for our Systems Design Lab, we're going to take a look at processing and evaluating, which is our application portion of the investigation. First of all, it's important to design a data collection table and to include qualitative as well as quantitative data. Now, as you are collecting data, your simulation will continue to show you a graph as it builds out the changes that you have manipulated. It will graph this for you. That's not enough. Simply screencasting this is not enough. We do actually need you to collect the data and present the data and practice that skill. As you do, as we change variables with the population, so as I said, it will graph it, but also you can see qualitatively what is happening as you observe the graphic of the fish population. So as we're thinking about observations, some thinking about as well, how many variations are you going to include or scenarios are you going to include, and how many trials would make sense, given that this is a simulation? Leave that to you. Also, as we process our data, you're going to make a graph. We have already done twice before graphs with Desmos, and where we have found the equation of the line, and where we have found r squared, and noted how close to r squared, how close our r squared value is to 1, and trying to make some meaning of our data on the basis of that statistical value. So we're going to do that again. As you conclude your investigation, you want to describe everything that's gone on. You want to make a comment about the validity of your hypothesis. Did your investigation demonstrate your hypothesis in a supported way? Was it correct? Or was your hypothesis demonstrated to be incorrect or unsupported? Either way, what are you basing that on? So you can describe the trend in your process data in terms of the shape of the line and everything else I just said about the equation of the line, r squared, what it means. You can also go back to the scientific reasoning that you pulled forward into your hypothesis. Again, when you are explaining with scientific reasoning and evaluating, you need to include Peel. So it's a really great structure to remind yourself that you are explaining, not just stating or describing. So again, state, this happened, describe, this happened and here's the details, and explain, here's how this happened, here's the details, and this is why it all took place. The final part, and this is new with this investigation, is to include an evaluation. So you're going to evaluate the validity of your experiment, anything that was an outlier, something that behaved in an unusual way. And you might also find that sources of error took place. Now we're using a simulation, so you might not see too much here. Note that a source of error is not a mistake. It's not something that you could have done differently but chose not to, or it's a mistake that you noticed but didn't go back to correct. That's not what we mean by sources of error. We mean sources of error, things that you can't have predicted heading into the experiment. So curiosities or issues with the measuring equipment or the technique, ways that you had intended to control variables, but you couldn't actually do them that way. Some reason why you couldn't collect enough data to make a valid conclusion. One place you might think about is, does the simulation limit you in any way in terms of collecting enough data? Another thing that you can do is thinking about an improvement and an extension. Is there some new question that arises based on the outcome of this experiment? Or are there other variables that might be interesting to explore in terms of their impact on population growth of the tuna? In either case, you're going to describe why that would be an interesting extension and some sense of what you think would be taking place.